So now, great. So now what do we do? I have a formula for something I knew perfectly well how to compute without all this fancy stuff. And the way we will do this is we will find a better way of using this information. And that will be called a determinant. If you remember, the way you evaluate a determinant in simplest rules is you have some kind of rules in which you multiply elements. And since Newton, we know that that's an expansion in the traces of determinants and power of the traces. The cute thing is that we'll be able to read off the determinant just by looking at the Markov graph or transition graph. So, what's a determinant? If you look at determinant of 1 minus zt, that's a polynomial in z, and what it is, it's the product of all the roots. Number of distinct roots is no larger than the dimension of the matrix, and often it's much smaller. And every time this thing vanishes, the zeros, the alpha, are the inverse eigenvalues. You can find the zero of the determinant. I will find, for each zero, I'll find the eigenvalue. Now, what does that have to do with our trace formula? The left hand is a trace of this evolution operator. Remember, we did this, and you must have done it other times. We can write a determinant as exponent of trace of log of the matrix. This is an identity for all finite matrices. And you might have seen in the form that a determinant of some matrix M is E to the trace of logarithm of the matrix M. Or that a logarithm of determinant of matrix M is the same thing as a trace of a logarithm of matrix M. I think we did it as a problem set, but everybody who does physics needs to know this identity because it's used all the time in statistical mechanics, quantum mechanics, etc. So that means that if you know traces, we should know also the determinant, and that's why we worked out traces first. The trace is the very succinct statement that says a property which is global, counting all cats, is done from the local properties, how each cat ran around. Now, this we can write as a logarithm, right? We can write this as exponential of minus. There is a 1 here, and this minus is convenient, so if you remember, log of 1 minus x is the sum of x minus sum of x equals 1 to infinity 1 over x to the n power. So we use this expansion here, and we got z of n divided by n trace of t transition matrix to the power n. So if we know how to take traces, we will know how to do the determinants. As you know, whenever you have exponential of a matrix, you can expand it as in a cumulant expansion. So you can write this as 1 minus the first term is just z over 1, so there's a z, trace t, and there'll be a minus c squared, something that is quadratic, and I'll pick up two terms. There'll be this term traced to the square. So by the first term will get squared in this expansion, that gives me this, but I also pick up trace of the matrix to the second power. So the main message is, if I know the traces, I can compute determinants. But now here comes a thing that follows the famous theorem of Hooft and Weltman. He says combinatorics cannot be taught. This is one of these things that you'll have to go into a room by yourself and emerge having understood it. And the claim is the following, that when you look at determinant, the traces that we deployed here will show up in a very beautiful way. As you walk on your Markov graph, you'll call each closed walk a loop or periodic orbit or cycle. And if the graph is sufficiently big, there could be several loops in different parts of it that don't cross each other or don't have any points in common. They'll be called non-intersecting loops. So there'll be sum of f, k equals 0, as many non-intersecting loops you can fit. And then each one will carry that little trace that we have developed here that tells us, what the prime walk is. We'll put a little thing here saying I sum up over all prime walks which are distinct. So I'm not allowed to repeat any walk twice. So this is a determinant of the graph, and must be totally obscure where it came from when I do it like this. So I think I have to work out a few examples before it starts making sense. But as you'll see, it'll be quite powerful. And it might answer your question. You might wonder, it's a finite matrix, everything is finite on the left-hand side. Why am I allowed to sum over infinity of graphs on the right-hand side, prime cycles? Because on the right-hand side, I'm allowed to take any binary sequence of any length. So what gives? What's going on? And it'll be precisely this property that f is the number of non-intersecting loops.